Hello everyone. So in continuation to the topic of coordination compounds, let us move ahead. Whenever we are discussing coordination compounds or complex salts, the very first that we think about is the effective atomic number, which is already discussed in one of our lectures, and the link is also available over here. Now we will be talking about three things. One is the hybridization, second one is the geometry, and if time permits in this particular lecture we will be talking about the magnetic properties. See, whenever we come across this word geometry and hybridization, these two go hand in hand when we are discussing it with the concept of coordination compounds. If I say that based on the ligand, we have Ml4 type of structure, or based on the ligand, we have Ml6 type of structures, then these two structures will help us deduce different hybridizations and different geometry. Ml6 will always refer to a octahedral geometry complex, and it will indicate two different types of hybridization, that is D2sp3 and sp3d2. On the very other side, if I have Ml4, it will be further divided into two different geometry. One is the tetrahedral geometry and second one is the square planar geometry. The tetrahedral geometry will then refer to sp3 hybridization, and the square planar geometry will then refer to dsp2 hybridization. So friends, we should get an idea that whenever we are trying to solve a coordination compound or a complex salt, we should have a basic idea of all these types of hybridization and geometry. Apart from all this, let us be very clear that there will be an instance where sometimes we will get a molecular trigonal bipyramidal, and when we have this trigonal bipyramidal type of geometry, we will be somewhere around sp3d hybridization. So let us begin with few well-known popular examples and try to solve through a proper method. Let us take the first example. We will start with a very popular complex, that is K4FeCN6. The first step that is ever involved while solving a coordination compound is to get the oxidation state of the central metal atom. If I go directly in a single shot, keeping into consideration that the earlier class was fruitful and is done completely by you, the oxidation state is 2. But if I need to explain it for a while, as potassium is +1 and you have 4 such potassiums, it will be +4, and you will have 4 negative charge on the top of this coordination site, leading to 4 to the power minus. As this is +1 multiplied by 4, it is +4. To maintain the electrical neutrality, I have to place -4 over here. Now, according to the mathematics, Fe plus 6 times sino has a -1 charge, and the one that is on the top as a superscript must be on the right hand side. If I solve this simple mathematics, it is -4 plus 6, leading me to +2 oxidation state, which was already mentioned. And I expect from the learners that we should be very much profound in getting this answer in a single shot. Once I have this Fe2+, I must always know the electronic configuration associated with the simple atom and its ionic state. For example, I take Fe, then I will be writing argon 18, 3d6, 4s2, 4p0 and 4d0. Friends, always keep one thing in mind, you go up to 4d. Why? You will get an idea very soon today. But if I say Fe2+, it means I should not write this, because 2+ means electron loss is going to occur, and there is a loss of 2 electrons always remember the loss will start first from 4s and then it will come to 3d. Therefore, argon 3d6, but both the electrons from 4s will be removed. 4s0, 4p0 and 4d0. Now, we should always identify the ligands into two categories. Excuse me. Those two categories are strong field ligand and weak field ligand. If we do not consider any exceptional cases, I will always write cyano as a strong field ligand, NH3 as a strong field ligand, and carbonyl as a strong field ligand, and rest of all as weak field ligand. And if you have any confusion in this, you can refer some standard book, or even if you can go through the +2 classes book, they have mentioned it very well. And believe me, whether you are appearing for a PET or SLET, up to an extent net, +2 books are very much important. Now, I have to mention this Fe2 plus in the form of writing. So, we all know that D has 5 orbits, S has 1, P has 3, and again the D has 5. But as we all know that there are 6 electrons over here, I will mention it like this. Why I did not mention 2 together? Because it is on the basis of the Aufbau, Hund and the Pauli rule. Now, be very clear that when I have 6 ligands, it falls in the category of octahedral. When I have 6 ligands, it falls in the category of octahedral. So, the first condition comes over here is 6 ligands, octahedral. Second condition comes over here is cyano. So, friends will write strong field ligand. And many of us, including me, in my earlier days of learning, used to directly pair over here. It is right, it is not wrong. But sometimes it can lead you to a wrong option of the answer. Henceforth, always once you have 6 ligands, octahedral, strong field or weak field, do not write anything directly. Just split your 5d orbitals. So let us start splitting it. Always remember the d orbitals get splitted into 2 sets, T2G and EG, where T2G has 3 and EG has 2 orbitals. You have to again fill the electrons in the number 6, following completely the Aufbau, Hund and Pauli rule, and therefore 1, 2, 3, 4, 5 and 6. Friends, we all know that when there is an existence of a strong field ligand, pairing takes place, and this pairing always moves from a higher energy level to a lower energy level, subject to condition that in the lower energy level there are empty orbitals. Can we find empty orbitals over here? Let us check. Yes, this electron will settle here and this electron will settle here. Therefore, the electronic configuration will look like all 6 electrons at the bottom line, no electrons in the top. So it is T2G and EG. Friends, I hope you are getting it. So I can now write T2G6, EG0. So I can see that all the electrons have been paired in the lower energy level of the orbitals, and therefore you can mention that these electrons shift to the inner orbitals, and therefore Fe2 plus looks like I am again drawing all the orbitals, and now you will get an idea why Sir has mentioned to go up to 4D. 1, 2, 3, 4, 5, 6, because the pairing has occurred. Therefore, 3D 4s, 4p and 4d. Now, how many ligands are present? 6. Each ligand donates 1 electron pair, so you are supposed to donate 6 electron pairs. So let us check. First electron pair, second electron pair, third, fourth, fifth and sixth. This 6 electron pair lead to a conclusion that the hybridization is D, 2 orbitals of D, therefore D2, 1 orbital of S and 3 orbitals of P. So it's a D2 sp3 hybridization. It's a D2 sp3 hybridization. So my answer is this. Now, what all things could we get out with just one simple workout of 2 minutes if we are doing it alone? Number 1, if my molecule is K4 FeCN6, the first thing I came up with is I have strong field ligand and that strong field ligand is cyno. Second is the oxidation state of Fe and the oxidation state of Fe is +2. Third thing is, in the previous lecture, you were doing this electronic configuration. Today you have a newer type of electronic configuration, that is T2G6 and EG0. Sometimes it is asked. And so today I have a newer type of electronic configuration, T2G6 EG0. The fourth thing is hybridization, D2sp3. Remember, when it is D2sp3 or sp3d2, the geometry is always octahedral. One more important thing that comes over here, that the ligand that is going to attack on the orbitals of metal has used 3d orbitals and not 4d orbitals. Remember very well, when the ligands attacking are utilizing the 3d orbitals and not the 4d orbitals, it is always coined as inner orbital complex. Inner orbital complex. When the pairing takes place and all of your electron comes and sit in the lower energy level, when pairing takes place and all of your electrons come and sit on the lower energy level, we always coin it as low spin complex. Friends, just one set of theory, and I am confident that the learners, the people who are associated with us for this particular session, can answer 7 to 8 different category of question depending upon their way of understanding. I can say that it has a strong field ligand. As it is having a strong field ligand, it gets paired. If it gets paired, it's a T2G6 and a EG0. All electrons are in the lower set of orbitals and hence it's a low spin complex. Apart from all this, it's a D2sp3 hybridization. As it's a D2sp3 hybridization and it is using the inner d orbitals, that's the 3d, it is called inner orbital complex and hence it's an octahedral geometry. So friends, this is how one simple complex can help you attain all these set of questions. I hope you are okay with this theory. If you are okay with this question, you can just rewind the video and look it once again, because now when I'll be going with the second question, probably I'll be going a little fast because I want you to learn all the possible structures in this single video so that in the next video I can serve you something else. Let us check. Now I'm changing the question and now my question is Fe H2O6 2+. Friends, looking just to this question, you will be very confidently able to say that H2O is a weak field ligand. Second thing, as H2O has electronic charge 0, 6 into 0 will be 0, so directly the oxidation state of Fe will be 2. Friends, writing the numbers in Roman letters always suggests its oxidation state. So Fe over here has the oxidation state +2. Now, as Fe is in its +2 oxidation state, its electronic configuration has to be argon 3d6, 4s0, 4p0, 4d0. Now be very perfect while writing these notations in the form of suborbits and orbitals. This is 3D, 4s, 4p, 4d, 6 electrons. I am strictly following the set of Aufbau, Hund and Pauli's rule. Then you have to mention it is a weak field ligand. No pairing occurs. If no pairing occurs, then this D6, which is going to divide into two, T2G and EG. Friends, you will say, why T2G and EG? Because it's an octahedral complex. Why it's an octahedral complex? Because it has coordination number 6. So whenever your coordination number is 6, it is always an octahedral complex. Whenever your coordination number is 4, it's always a tetrahedral or a square planar complex. So I have 6 electrons like this. No pairing takes place. As no pairing takes place, the electronic configuration will be T2G4, EG2. And therefore, it is as such written again with no pairing. Therefore, it's a 3D6, 4S0, 4P0 and 4D0. I have seen many different papers where questions from this topic comes. No pairing because of weak field ligand. Now how many ligands you have? 6. So they will not come and fill over here because an orbital has a maximum capacity of 2 and these 3 have 1 electron filled, so 2 more electrons cannot be accommodated. So electrons will start getting filled from this particular point. So it is sp3d2. So now you have a new set of hybridization, that is sp3d2. So it is sp3d2, it is again ml6, it is again octahedral, but as you have the 4d orbitals getting accumulated, it is no more inner orbital complex, it's an outer orbital complex. Apart from calling it outer orbital complex, friends, there are electrons present in the higher energy level, so it will be again a high spin complex. I hope you are clear. So in short, there are a few tricks which will not get okay with Yon-Taylor distortion, but in all other places it will work. Whenever I say that I have a strong field ligand, not a weak field, this is a weak field, strong field ligand, it will mostly be inner orbital complex, mostly be a low spin complex. But when I have a weak field ligand, it will mostly be outer orbital complex, it will mostly be a high spin complex. Whenever I have a strong field ligand, it will utilize 3D. Whenever I have a low spin, whenever I have a high spin or a weak field ligand, it will always utilize outer orbital, that's the 4D. So this was the second question from the same category of octahedral. So as of now, we can say that we have done both the category 1-1 question, but now is the time to involve Yon-Taylor distortion, that's an exceptional case. Let us see what comes out from this exceptional case. I have seen multiple papers asking such kind of questions. So let us start with the third question. It is Ni CN6 4 minus. I am planning to do 2 numericals and I am planning to show you that in few cases the weak field and strong field ligand do not matter in any way. When it does not matter, that is the question to be asked. I will go a little fast. If you did not get somewhere, you can ask me afterwards because time matters. So over here, the state of nickel will be +2. Over here also, the state of nickel will be +2. If the state of nickel is +2 in both the cases, it will always be 3d8, 4s0, 4p0, 4d0. There is an argon present, don't worry. Again a 3d8, 4s0, 4p0, 4d0. Now be very precise. I have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Similarly over here I have 8 electrons to be placed Friends, let us split this into two sets. T2G and EG. Eight electrons. When I place these 8 electrons over here, it is like this. Going on the other side. This point will make you understand why we do not directly pair from here. We always go for T2G EG concept. It is very important over here. Believe me, if this was not there, looking to just these two examples, many of us would have paired this electron over here because it was a strong field ligand and pairing take place. And if that would have been done, we would have erupted out with a new class of hybridization, DsP3D, which does not exist. But when you go for a splitting of d orbitals, this is called a splitting of d orbitals, you will come to know that all the lower energy level orbitals are completely filled with electrons. When the lower energy level orbitals are completely filled with electrons, you cannot come down. And also, pairing does not occur in same energy level. I cannot say that over here we have a weak field, so do not worry, but over here as you have a strong field, pair it like this. No, you cannot pair like this because it is the same energy level. And friends, these 5 are not in the same energy level, and that can only be understood when you split these 5 into 2. So it's very clear. Remember me, remember this lecture, remember this thing and note it down in your book that when you have a D8 kind of a geometry, D8 kind of an electronic configuration, whether it's a strong field geometry or whether it's a weak field geometry in the octahedral complex. Why in the octahedral complex? Because the coordination site is 6, so it's an octahedral, it's an ML6 category. No role of a strong field ligand can work. It's always a simple theory. No pairing can take place in the same energy level. So the electronic configuration over here will be T2G6EG2. The electronic configuration over here will also be T2G6EG2. Now, be very precise in writing, not show even a single existing pair, whether it's a strong field or a weak field when it comes to the D8 kind of a complex, because of no pairing taking place in the same energy level, which is known as Yohn-Teller distortion. The spell starts with J, which is silent, so it's a Yohn-Teller distortion. Therefore, as there are 8 electrons over here, 8 electrons over here, don't get confused, I'm doing 2 numericals at a time. The 6 ligands will not be filled at these 2 points, but I'll start from this point filling up of the ligands. When I'll start from this point filling up of the ligands, the chemistry will change, and therefore it is sp3d2, sp3d2. So the hybridization will be sp3d2, whether it's a strong or whether it's a weak. There is no importance of that strong weak ligand chemistry over here. As the D4 is used, that's the 4D is used, I will always spell both of them as outer orbital complex. Over and above, apart from outer orbital complex, I am also going to say that as there are electrons in the higher state, it's a high spin complex. So I hope you are clear with these 2 theories, and we can deduce from these 2 theories that whenever you have D8 type of a geometry, no matter whether it's a strong field, no matter whether it's a weak field, our answer is very clear, and that answer of ours is outer orbital complex, high spin complex, sp3d2 octahedral. So I hope I have made this section clear to each viewer and subscriber available with me on this channel. Our examples that we took was K4 FeCN6. Even we had FeH2O6 2 plus 1, 2, 3 and 4. I hope I am clear with this section. Now we will be solving the second category of R's, that is this. So let us move ahead. Let us check another example. I hope you are getting it, and if you have any query, you know where and how to contact me. Let us take another example, the example number 5. I am going to use NiCl4 to the power 2 minus. Whenever I am using NiCl4 to the power 2 minus, Ni is always 2 in its oxidation state. Why? Ni plus 4 into minus 1 is equal to minus 2. So mathematics makes us aware of it being plus 2. Now, when you have Ni in its plus 2 state, you are very clear that it's argon 3d8, 4s0, 4p0, 4d0. Be very clear. I am repeating the things, but now there will be few changes that will take place. Friends, coordination number is 4. So when the coordination number is 4, it is no more Ml6. It is now Ml4. When it is Ml4, you have two choices: the geometry to be square planar or the geometry to be tetrahedral. Which one to select? In most of the cases, if at all Young-Taylor distortion is not there, the exception that we saw just now, for a weak field ligand, your answer should always be tetrahedral and sp3. For weak field ligand, your answer should always be tetrahedral and sp3. Let us check. We have chloride over here, and chloride, which is pronounced as chlorido when it comes to inorganic coordination chemistry, is a weak field ligand. Here, chlorido is a weak field ligand, so no pairing occurs. Let us check. Again, I am not going to represent 3D as such. I will split it. But friends, when I was splitting an octahedral complex, it was T2GEG. But when I am splitting a tetrahedral complex or a ML4 complex, it will never be T2GEG in the case of tetrahedral. Why I use the word that I am splitting a tetrahedral complex? Because I know it's a weak field and it will going to be lead me to a tetrahedral complex. It is always mentioned as EgT2G. It's not T2GEG, it's EgT2G. And Eg represents two set of orbitals, dx square minus y square and dz square, and T2G represents three set of orbitals, and they are dxy, dyz, dzx. Now, therefore I'll mention 2 orbitals over here and 3 orbitals over here. 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now you know better than me. Sir, you cannot pair these 2 electrons. Why sir cannot pair these 2 electrons? Because these 2 electrons are in the same energy level. Number 2, it's a weak field ligand. So leave it as such. Now I am leaving it as such. I am moving ahead, and when I move ahead, I have coordination number as 4, all unidentate ligands. So one pair of electrons will attack onto the central metal atom of my complex, and it will lead to 4 ligands attacking. 1 from S, 3 from P, and friends, it's an sp3. When it is an sp3 hybridization, tetrahedral will be its geometry, it's a weak field ligand. Now, you cannot say this to be a high spin complex, you cannot say it to be a low spin complex. Why? Because there is no utilization of 3D by the ligands, there is no utilization of 4D by the ligands. So remember very well, be very precise that the weak field or the strong field which relates to the high spin complex and the low spin complex, or the inner orbital complex and the outer orbital complex, only works in the ML6 category. It does not work in the ML4 category when it comes to the tetrahedral complex. So I will simply write it as a coordination compound or a complex salt having the hybridization sp3, having the geometry tetrahedral. I will not utter a single word that it's a high spin complex or a low spin complex. I will never speak it to be an inner orbital complex or an outer orbital complex. So I know the geometry, I know the hybridization, yes, EG4, T2G4. So the new electronic configuration in the format of EG-T2G is now known to me. I'll write EG4 plus first, T2G4 then. So friends, hope you are getting it. So this was the third thing that I came across. So we are done with 3 concepts. Still we are left with this 4th one. But this is highly important. This is very, very important. That what happens when you have a square planar kind of geometry. Let us check. Friends, never think that we will discuss each and every single example. I am here to give you an idea. It is your job then to go through different books, find the questions, solve them. Nevertheless, I am going to keep on solving and updating videos, uploading videos on different questions, but that not means that I am going to go with all questions. I am going to go with all type of questions. Number of question is your responsibility. So, Ni CN4 2 minus. Looking to the molecule itself, you get an idea that the coordination site is 4. Cn helps you finding it to be a strong field ligand. So the coordination site is 4. It's a strong field ligand and its oxidation state is 2. So it is Ni in its 2 plus state. Again, I am going to go a little fast. Ni in its 2 plus state. So I will just mention it to be 3D8, 4S0, 4P0 and 4D0, and just quickly formatting the suborbits and the orbitals, I can clearly mention like this 3D8. Once I am done with this, I have to look into this strong field ligand and the coordination site. Now be very clear. When coordination number is 4, it is a strong field ligand. Split it first. But wait a while. Strong field ligand, coordination number 4, split it first like octahedral, not like tetrahedral. Split like octahedral. Then splitting like octahedral will give you an idea. T2GEG. And then when you will fill up these, it will be something like this. And you will say, sir, pairing will not take place. Why? Because the energy are in the same level. You are right, but not completely. As it is coordination number 4, as it is a strong field ligand, as it has started the splitting like octahedral, which belongs to the ML6 category and not ML4, a resplitting will take place. See what happens. I am going to deliberately draw it again to make the concept much more clearer. It is an 8 electron system which got splitted like this. I will not stop here. Again splitting again splitting. Now the two orbitals when get splits into two energy level, one energy level, one energy level. Three orbitals when get split into two level, two energy level, one energy level. I have a task for you. I will name these as T2G and EG. I will not name these four. I wish you people to name it. What happens over here? There are 6 electrons over here. So it's 1, 2, 3, 4, 5, 6. Don't get confused. These two levels belong to T2G and therefore I have added electrons first over there. And one over here and one over here. So ideally what happens is, as it's a strong field ligand, this will fall down and it comes over here. So friends, pairing is occurring. Pairing is occurring. Why did pair occur? Because it was splitting like octahedral, strong field ligand, coordination number 4. And now if you check properly, one complete orbital is empty. It means as it was a splitting of a splitting, the electron could be paired up. As it was a splitting of a splitting, electron could be paired up, and therefore we can now mention these as, it is T2G6, EG2. You cannot make any change over there, but you can go a step ahead and give me a newer answer. 1, 2, 3, 4, 5, 6, 7, 8. Now 4 ligands are supposed to attack first, second, third, fourth. So it is DSP2. Simple. So the hybridization has changed. It is DSP2. So when does DSP2 occur? When it's a strong field ligand, when it's an ML4, when the splitting is like octahedral, and I know that it's a splitting of a splitting, I will always end up with DSP2. So be very clear. I have justified this DSP2, and justifying this DSP2 will again give me a square planar geometry. So friends, we have gone through a very anticipated topic in chemistry where just by simply knowing a complex, we could find out the oxidation state, we could find out its electronic configuration, we could find out its T2GEG electronic configuration, it's a geometry, it's a hybridization, whether it's a low spin or high spin complex, and whether it is an inner orbital complex and an outer orbital complex. If you have any queries, you can tune me up. Be in contact. Stay tuned. After this video, there will be another video coming up of coordination compounds, which will involve 2 important things, of which one is its magnetic properties, a very important aspect. Thank you.